Okay. In today's class, as I said, we'll discuss torque acting on a current carrying loop and how a galvanometer is constructed. But before that, let us discuss one question. Consider a circular loop like this. Assume it carries a current I. And let's say we switch on a magnetic field, uniform magnetic field, directed into the plane of the screen. Okay. Yeah, those of you who just joined, the class just started. So this is the first question that we are discussing. A circular current carrying loop. Okay, assume its radius is R. Carrying a current I is placed in a uniform magnetic field. And as you can see, magnetic field is into the screen, that is, it's in the Z direction. And the current loop is in the XY plane, in the plane of your screen. What does a current carrying loop behave like? Anyone?
A dipole, sir.
A magnetic dipole. And when you place a dipole in a uniform magnetic field, what is the net force experienced by it? Net force on a current loop in a uniform magnetic field. How much will that be? See, it's a current wire, okay? But it has been bent in the form of a loop. Now, if the magnetic field is uniform, net force on a current wire generally is I L cross B. Okay, in a uniform field, it is I L cross B. For a closed loop, L vector becomes 0. So the net force on the current loop also becomes 0. We had discussed this in the last class. We even, not last class, the class before that. We even compared, or we even recollected how an electric dipole experiences net zero force in a uniform electric field. Okay. Similarly, magnetic dipole experiences net zero force in a uniform magnetic field. Okay. But I want you all to consider element by element. For example, let's say we consider this current element. You all think about it. Let's say the current element is ideal. It's in the plane of your screen, as you can see. Magnetic field is perpendicular to your screen. What is the direction of the force acting on it? Force acting on a current element is dF is equal to IDL cross B. Okay. Based on that, tell me the direction of force acting on that element. Isha, what do you think is the direction of IDL cross B here? Yes.
Sir, like it will be perpendicular, sir.
Perpendicular to?
The loop, sir, like ideal, sir. Like
Perpendicular
to
to ideal. Okay. Will it be outward or inward?
no, like it will be now. Suppose if you consider for this, it will be the at the top left corner, sir.
So is that radially outward for the loop,
Radial
or
outward, sir.
that is what I'm asking. And that's correct. See, ideal cross B, you just need to take the direction of cross product, place your right hand fingers along ideal, curl them into your screen. You'll see the thumb pointing radially outward. Okay. Or you can do it the other way also. Keep your thumb along the current element, fingers along the magnetic field. Okay. Then palm will face radially outward. So you can say that the force dF acting on this element is in this direction. Okay. Similarly, if you consider other elements of this loop, say one element here, for that element, the magnetic force acting will be this way. Likewise, you can imagine force acting on other elements also. Maybe one element here, and so on. they'll all be experiencing small forces in the radially outward direction. And as you can see, for every df, there is an equal and opposite df which balances it. That is why the net force on the current loop is 0. Fine. IL cross B, it becomes 0. That doesn't mean there is no force at all. There are forces acting at different parts of the loop, but they're all balanced. They'll all get cancelled. Okay. Now this is a current wire. Okay. And there are forces acting radially outward at every point. Will this wire feel stretched or not? Will there be tension developed in this wire or not?
So there will be tension.
There will be tension, okay, because at every point we are pulling it radially outward, the wire will feel stretched. Okay, so there will be tension. The question now is to derive the tension in this wire. Okay, so see, the same question, if they ask you in the exam, they'll directly give you this situation. They'll say there is a circular loop in a uniform magnetic field, calculate tension. You will have to do all this visualization. You should think what happens when there is current in a magnetic field, when there's a current wire in a magnetic field. Why should there be tension in the wire? Okay, all those things you'll have to think on your own. That is the difference between class and exam. That's why many students find difficulty while answering questions or solving problems in the exam, because they directly ask you the final result. Anyway, we know that there are forces acting on this wire radially outward. We can even tell the magnitude if needed, because df is idl cross b. That's the vector notation. But if you only want the magnitude of the force, it will be idl b sine 90 degrees, because every dl vector is in the plane of your screen. Magnetic field is perpendicular to your screen. Angle between them will be 90. So the force is idl b on each element. But the problem is to derive the tension in this loop. So can any of you tell me an idea how to do that?
Sir, can we use stress here, sir? The concept of stress.
How?
So like it is a wire, right?
It is a wire.
If we visualize, we can see that it is expanding, sir.
Yeah, due to tension, because it is being stretched radially outward, it would expand a little bit. But the question itself is to calculate tension, no? Yes, if you want to use stress to calculate tension, you need to know stress, to know how much stress is generated in it. Do you know any expression for that?
No, sir, like stress is like force acting per cross-sectional area in a wire, right?
That's correct. If you want to find stress is force per unit area, perpendicular force per unit area. The question is to calculate that force, no? So
Yes,
from the equation that you said, if you want to calculate the force, you need to know how much stress is generated in the wire. Is there a way to find that out? Okay. Any idea, anyone? We know with what force each element of this wire is being pulled outwards. Okay. We know the expression for this df. And you are asked to calculate the tension in the wire. What can be done? I'm sure you must have solved questions like this in surface tension also. In surface tension, what they do, they put a loop of loop of wire, okay, on a liquid film, and they poke inside. When you poke here, what happens is this part of the surface disappears, and the outer surface will be pulling the wire outwards, and it will become a circle. I'm sure you must have derived tension also in that case. So, okay, fine. First of all, are you all able to visualize that there will be tension generated in it? Okay, it's like, it's like there are forces pulling the wire radially outward at every point. Okay, so it will feel stretched. There will be some tension generated in it. That tension is what we need to calculate. I'll tell you two methods. Remember this, because questions like this can be asked in many situations. Many situations means a similar question can be framed in laws of motion. They can simply give you a ring, spin the ring with an angular velocity omega, and ask you what is the tension generated in it. Okay. Or in, as I said, in fluids, okay, they can put it on a film of soap solution, and the film of soap solution, due to surface tension, it will be stretching the wire. They can ask you what is the tension generated in the wire. The approach is same in all cases. So there are two ways. Listen, we know that there is a current, so I'm not showing the current. There is a current. Now there will be DFs acting everywhere on this wire, at every point of this wire. Okay. Yash is asking, is it force per unit length? No, we need tension in this wire. The force itself is what we want. Okay. Fine. DF is same everywhere because it's a uniform magnetic field. Okay. The forces acting on the wire, on each element of the wire, are same everywhere. Now, if the forces acting on the wire are same everywhere, do you all think tension will be uniform over the entire wire, or do you think tension will vary from point to point? If it is being pulled in the same manner in all directions, will the same tension be generated everywhere, or will some points experience greater tension than others? Mansa, what do you think?
Sir, can you repeat the question, sir?
If these DF forces are all same in magnitude, will the same tension get generated in the wire everywhere or not?
Maybe not, sir.
Why? Or at which points do you think the tension will be more?
At the center.
See, tension gets generated in the wire. The center is not part of the wire. Okay. There is a circular ring. That circular ring is being pulled radially outward like this at many different points. Okay, I'm telling this to all of you. So there will be some tension generated in that ring. I'm asking if that tension will be same everywhere or not.
Sir, it will be the same.
It will be the same. There is no reason why it should be more at some points and less at other points. Okay. All points are being pulled with the same force radially outward. So the same tension will get generated everywhere. Okay. What is the net force acting on this wire?
0, sir.
0. The resultant of all these forces is 0. That means the wire will be in equilibrium. If the entire wire is in equilibrium, even half wire will be in equilibrium. Okay, so let us visualize half of this wire. Okay, for now I will erase the other half. It's there, but we are only looking at one half. Okay. Tell me what all forces act on this one half of the wire. Anyone? What all forces act on this half of the wire? What are these vectors that I have drawn?
DF, sir.
What force is that?
So like
force?
force due to magnetic fields.
It's the magnetic force acting on each current element of that wire. So these purple vectors that I have drawn, they're all magnetic force vectors. Okay. We know that the complete wire would have been in equilibrium. Okay. Even this half wire would have been in equilibrium. Tell me, if you look at these purple vectors, consider all of them. What is the direction of their resultant on the half wire? What is the direction of resultant of all these DF forces on one half of the wire?
Radially outwards, sir.
Which way? Radially outward could mean like this, like this, like this. There are many possibilities, no?
Like at the point half of the semicircle.
Symmetrically it will be. Okay. See, there are a bunch of vectors here. They are all of the same strength. Okay. And they are distributed symmetrically. Then their resultant will be along the line of symmetry. Okay. So the total magnetic force acting on this semicircle is in this direction. That we could have told without visualizing all this also. Magnetic force on the semicircle will be I L vector of the semicircle cross B. For the semicircle, L vector will be from here to here. That's the L vector. Magnetic field is into the screen. Then if you do L cross B, your thumb will point in this direction, and this will be the direction of force on the semicircle. Okay, we could have told that way also. But last class I told you, you should imagine forces element by element also, not just on the entire system. Okay. We know that that half of the wire would have been in equilibrium. What holds that half of the wire? What I mean to say is, had it been a full wire, full circular wire, every part of the wire would have been in equilibrium. So that semicircle also would have been in equilibrium. Equilibrium means net force being 0. So had it been a full wire, which force would have cancelled this magnetic force on the semicircle?
Like the vector which is opposite to the yellow vector.
Which vector is opposite to the yellow vector?
So like the magnetic force vectors.
No. On this semicircle, this yellow vector is the magnetic force. The other semicircle will have another magnetic force acting on that one. Why will that force balance this one? No. That second yellow vector is acting on the second semicircle. This first yellow vector is acting on the first semicircle. On the entire system, if you see, yes, on the full circle, this force is balanced by this. That I agree. But if you only consider one part of the system, only consider that semicircle, what is balancing the magnetic force?
So is it that the intermolecular forces?
Kind of. It is the intermolecular force, correct. See, just a moment. Consider the other semicircle also. This way. On the other semicircle, there will be a magnetic force acting like this. Okay. So effectively what this magnetic force on each semicircle does is it tries to separate them. But there is something holding them. Okay. Let's mark one point here joining the semicircles and one point here joining the semicircles. As Yash was saying, the intermolecular forces within the string, within the wire, they hold the two pieces of the wire together. Okay, not just these two pieces of the wire. In fact, you can consider any two semicircular parts of it. Okay, let me remove these forces. You consider this semicircle and this semicircle. There will be magnetic force pulling this semicircle this way, this semicircle this way. Then the intermolecular forces at this point and this point will be holding them. Okay, and that intermolecular holding force is what we call as tension. Tension is what keeps the wire intact. It doesn't allow the semicircular parts to separate. It doesn't allow the elements to fly off in different directions. Okay, the intermolecular force between the elements keeps them in place. Okay, maintains the shape of that circle. Anyway, we know the magnetic force pulling this way. It is I. L vector for the semicircle is 2 times the radius multiplied with B. We know the magnetic force pulling the other semicircle also, but let it be. That doesn't matter. Now tell me, on the upper part of the loop, like the first semicircle, magnetic force is trying to pull it away like this along the yellow vector. Okay, these small elements, these small force vectors, together, they're trying to make it go this way. What is preventing that semicircle from flying off or moving off in that direction? Intermolecular forces, that is tension. So at these red dots that I have marked, there will be one tension acting this way and one tension acting this way. Okay, you all need to understand the basic idea of tension. Listen, all of you. Suppose there is a rod. You stretch the rod by pulling it or by applying an outward force on both sides like this. You try to stretch the rod. Will the rod simply break off if you pull it at both ends? You can even try that on the pen that you are holding. You try to pull the ends of the pen outwards like this. Will the pen simply break off? What do you say? It does not. Okay, you are trying to separate. For example, you can imagine a boundary anywhere along the rod. You can imagine a boundary, say here. There will be one molecule on the left side of that boundary and one molecule on the right side of that boundary, and they have a bond between them. Okay, or intermolecular force will be there. I should not call it a bond. Okay, you can call those molecules as A and B. So when you try to separate them, the intermolecular force between them keeps them together. Okay, so basically what is happening, A will be pulling B and B will be pulling A. That pulling force generated inside the system is what we call tension. Okay, so if you consider only the left side part of the rod, say from here to here, if you consider only the left side part of the rod, we are pulling it with one force on this side, but it's not going off that way, no? It is staying there. Why? Because of the tension it experiences here. B is pulling A. Okay, so there will be a tension on it. Similarly, the other part of the wire, the smaller part, if you consider, we are pulling it with a force F on this end, but it doesn't go away, no? Why? Because A is holding B. So A exerts the same force of tension on B like this. Okay. So there will be tension generated here. Now come back to the question. There are small forces, DFs, acting everywhere on this loop. But if you think of it as two semicircles, the sum of all DFs acting on one semicircle, we have indicated with that yellow vector. Now, due to that yellow vector, that yellow force, that magnetic force that is there, that semicircle should have gone off that way, but it is not going. Why? You can imagine it like this. Okay, let me show molecule by molecule. Just a moment. You can take one molecule of the upper semicircle, one molecule of the lower semicircle, and on that side also, one molecule of the upper semicircle, one on the lower side. They will be holding each other. Okay, so if you consider only one of those semicircles, there will be a tension acting on it at 2 points. So let's consider that separately. So there will be one tension acting here this way and one tension acting here this way. Now, why did I take only semicircular part? Why didn't I take quarter circle or some other part? Because if we take a semicircle, these two tensions will be in the same direction. They'll be parallel to each other. It will be easy to add them. Okay, had I taken some other arc like this, first of all, calculation of magnetic force on that arc would have been tedious because we need to know this length vector. For a semicircle, the length vector is very easy. R, it becomes 2R. Okay, so calculation of this force is easy and tensions are both in the opposite direction. So you can directly write, in case of semicircle, you can directly write 2T balances the magnetic force. How much is the magnetic force? 2IRB. 2T balances 2IRB. So you'll get tension as IRB. in that loop. That's all. That's the solution. Had we taken some other part of the loop instead of semicircle, what difficulty would we have faced? First of all, getting this length vector is difficult, which means getting the magnetic force is difficult. Okay. And after that also, one tension will be this way, another tension will be this way. They're not in exactly the same direction. So if this is T and this is T, you can't say their resultant is 2T. We'll have to take their components and balance those components to the magnetic force. Okay, that would have been tedious. That's why we take a semicircular part. That is why in the first place I asked you whether the tension will be same everywhere or not. Because if it's same, how does it matter where you take? Okay, it is up to your convenience. So did you all understand the solution? First thing you need to understand is why tension will get generated in this loop. Next is how we calculated the tension. We made use of semicircular parts of the loop, half loops. Okay. So if you have any doubts, you can ask. Otherwise, after this, I'll tell you another method also to solve. Okay. Let us look at the other method to solve. Our aim was to calculate tension in this loop. Okay. Consider one element of the loop. Let's say from here to here. Now, if you join the ends of that element to the center of the loop, it will subtend a small angle. In the diagram, it looks like a large angle, but if the element is really small, it subtends a small angle. Call that angle as d theta. Okay. Now on that element, we know there is a magnetic force acting outwards. dF. We even know how much that is. dF in magnitude, it is IDL B. Okay. Now the radius of this ring was given as R, ring or loop. Radius was given as R. So we can write, can one of you tell me, if radius is R and angle is d theta, what can dl be written as? dl is the length of the arc. How do you express it in terms of radius and angle? Okay, L is equal to R theta, so dl is equal to R d theta. Rishi, Mansa, are you all aware of this or not? Like,
Yes,
do
sir. Yes,
you
sir.
know L is equal to R theta? Yeah.
Yes, sir.
So small length dl will be R into small angle d theta. So the force dF can now be written as, in place of dl, if I write R d theta, it becomes IRB d theta. That's the force, magnetic force. That's not what we want. What we want is the tension tension in this loop. Now listen, for this element also, at the edges or at the ends, there will be tensions acting. There will be a tension pulling it this way, and there will be a tension pulling it this way. Now these two tensions are not exactly opposite to each other because the element is curved. Okay, it's not a straight element that tensions are exactly opposite. It's a curved element, so the tensions will be making some small angle. So if you imagine the line of symmetry, okay, the line of symmetry is the line along which I have shown dF. The total angle subtended at the center, we took d theta, then half angle will be d theta by 2. This side also the half angle will be d theta by 2. Okay, why are we bothered about that angles? Again, consider the element. Say, okay, I'll just enlarge this for you to understand. Let's say this is the element. Okay, join the ends of the element to the center of the circle. There's one force. Okay, let's visualize the line of symmetry also. this angle is d theta by 2. If this angle is d theta by 2, tension also will be acting at an angle d theta by 2. Like if the tension acted here, it would have been perpendicular to that line of symmetry. But if this angle is d theta by 2, then tension also would have rotated by d theta by 2. If it makes d theta by 2 with that direction, then with the line of symmetry, it will be making 90 minus d theta by 2. 90 is in degrees, you have to write in radians. Let's take it as pi by 2. Okay, then what will the component of tension in this direction become? It will become T sine of d theta by 2. With the other side, it makes d theta by 2 angle. So that component would have been T cos d theta by 2. This component, radially inward component, will be T sine d theta by 2. Is this point clear to all of you? If you have any doubt, you can ask. Okay, let me just show the reference directions properly. Line of symmetry, I'm drawing it in yellow. And perpendicular to the line of symmetry, I'll draw it in blue. With that blue line, tension makes d theta by 2 angle. Then with the yellow line, because blue and yellow are perpendicular, it will make 90 minus d theta by 2. So its component in this direction along the yellow line, tension's component would be T sine d theta by 2. And there's one more tension on this side of the element as well. It will also have a component, inward component, the same T sine d theta by 2. So now if you combine these two tensions, these two components of tensions, effectively the tension pulling the element inwards is 2t sine of d theta by 2. Okay, that is pulling the element inwards. What is pulling the element outwards? dF. Okay, so tension components are pulling it in like this. dF is pulling it out as shown. That dF is balanced by these two tension components. Okay, so on a single element also you can write the balancing equation. Let us write the equation now. We know dF is I R B d theta. That's the magnetic force pulling the element outwards. It is balanced by these two tension components acting inwards. Okay, 2t sine of d theta by 2. Now d theta is a small angle, right? Then d theta by 2 also will be a small angle. One of you tell me, if x is a small angle, what is sin x approximately equal to?
X.
Sin x is approximately equal to x itself. Okay. Rishi, Mansa, are you aware of this? It's like
Yeah.
limit x tends to 0.
Yes, sir.
Okay, maths question actually. Sin x by x becomes 1. Sin x by x becomes 1 means sin x tends to x itself. Okay, when x is a small angle. So we'll use that small angle approximation here. So sin of d theta by 2 can conveniently be written as simply d theta by 2. Sin x is x, so sin d theta by 2 is d theta by 2. The 2's get cancelled. Then the d thetas can be cancelled on both sides. Therefore, you get t is equal to IRB. The same answer that we got when we considered semicircles. Okay. Now, why did I teach you both methods? See, this semicircle method will work only when tension is same everywhere. Okay. They generally, the question asked you generally to calculate tension in the wire. It means tension is same everywhere. Okay. So that semicircular method will work, and it's easy also. But suppose they put this wire in a non-uniform magnetic field, and then they ask you to calculate tension at a particular point. Then you will have to see the magnetic force acting on that particular element and calculate the tension at on both sides of that particular element. Then only this second method will work. That semicircle method may not work. Okay, so do this later once again on your own. Both ways try to solve this question.
Sir, can you show the first method one?
Can I?
Like the last one.
Last part.
The first method.
This one.
Yes, sir.
You want me to explain it?
Yes, sir. Like just
See, the question was to calculate tension in the wire. First thing we checked is if tension will be same everywhere. We know there are equal forces DF acting everywhere on this wire. So the same tension should be generated everywhere. So to make things simple, I considered one half of the wire. On one half of the wire, if you see, okay, let's say this half, there will be a magnetic force acting represented by that yellow vector. But we don't see that one half of the wire going away. Okay, the other half of the wire is holding it. How? By means of tension here and here. Okay, intermolecular attraction is holding the wire in place. Okay, so I visualize that semicircle separately now. Okay, only that one half of the wire, if you see, there is a magnetic force trying to pull it away. There are two tensions trying to hold it in place or holding it in place. So those two tensions should be balancing the magnetic force. So 2T is equal to 2 times of IRB. T becomes IRB.
okay.
Okay. See, this same or a similar question can be asked in laws of motion, as I said. Suppose there's a ring. Radius is R. Assume its total mass is M. Fine. You spin the ring about its own axis with an angular velocity omega. Now, if you visualize this ring as a collection of particles, okay, say one particle here, one particle here, one particle here, one here, and so on. When you spin it around, these particles will have a tendency to fly away. Okay, but when in the form of a ring, they don't fly away. Why? Because of intermolecular forces. They have a tendency to fly away tangentially, but each molecule will be connected to the next molecule. Okay, like this. Right? So what happens when you spin it around? Tension gets developed in those connections. Okay, so suppose you are asked to calculate tension in this case. I'll just briefly tell you what you can do. Consider a small element of the wire. Join it to the center. Same idea as before. One tension will be acting this way, one tension will be acting this way. Their components will be there, acting radially inward. So the resultant of those two tension components will be providing the centripetal force necessary for that element to move in the circle. So what you will do now is 2t sine of d theta by 2. You will equate it to centripetal force. Can one of you quickly tell me the formula for centripetal force in terms of mass and angular velocity?
mv square by r.
Angular velocity, I said. It should be in terms of omega. mv square by r is correct only, but it's in terms of speed. Okay. See, from mv square by r itself. Okay, you all need to
Sir,
stay in touch with.
mr omega square.
It will be mr omega square because v is
Okay.
equal to r omega, no? Square it. It becomes mr omega square. So here you will equate this tension's inward component to mass of the element dm r omega square. And then dm you express in terms of d theta, cancel d theta and all, you can find out the tension. But see, the idea is similar, no? And such questions you can get in surface tension also. Anyway, I won't go into all that now. Right. So that's one question I wanted to discuss today. Next, let us talk about torque acting on a current carrying loop in a uniform magnetic field. We know that the net force on current loop in a uniform magnetic field is 0. Okay, there will be DFs acting on every element, they'll cancel. Okay, but they can produce a torque sometimes. Just like an electric dipole placed in an electric field can experience a torque a magnetic dipole placed in a magnetic field can also experience a torque. Okay, and it has very important applications in engineering, science. Okay. So let us discuss the basics of it. For convenience, let's consider a rectangular loop like this. Assume the loop is in the plane of your screen. Let's say a current I passes through it or flows in it. One of you quickly tell me, what is the formula for magnetic dipole moment of a current loop? We had discussed this in the beginning of this chapter actually.
Sir, M into L.
See, M into L is in terms of pole strength.
Effective
Okay.
length.
Pole strength and effective length. These days that concept is itself not there in your textbook. Okay. This formula is correct only, but I asked you, what is the formula for magnetic moment of a current carrying loop? This ML can be used for a bar magnet. Okay.
Yes, sir.
For a
Okay.
current loop, it will be in terms of the current. Can any of you recollect the
I
formula?
into A, sir.
Correct. IA. If there are n number of loops, then it is NIA. If there's only one loop, it is IA. Correct. Correct. Fine. Let's say the length of this rectangle is L and the breadth is B. Then area becomes LB, L into small b. Then the magnetic moment becomes I into L into small b. Okay, let it be like that. What is the direction of magnetic moment? Magnetic moment is a vector quantity. How to assign direction to it?
Sir, it is usually taken from the line joining from the poles.
Where are the poles?
From South Pole to North Pole.
Correct. That is correct. Yeah, dipole moment is from south to north. Like electric dipole moment is from minus q to plus q. Magnetic dipole moment is from south to north. For this loop, which side is south, which side is north?
Sir, I think it may go from length, direction of current, sir.
You have to curl your right hand fingers in the direction of flow of current. Okay.
Yes.
If you curl your
So
right
it
hand
is
fingers
radially
like
out.
this, no, curl your right hand fingers like this, thumb will point inwards.
Yeah, sir, inwards.
Okay. And see, you don't have to be in a hurry to answer. Radial, that term is to be used when you have circular wire. Okay. For a rectangular wire, there's no word called this. I mean, radial doesn't make sense in case of a rectangular wire. In this case, if you curl your right hand fingers clockwise, you all can observe that the thumb will point into the screen. So magnetic moment is inwards. In fact, it's in the same direction as the area vector. Okay. For a current loop, we can assign area vector. The direction of area vector is the direction shown by the thumb when we curl our right hand fingers along the flow of current. Okay. Let us imagine a uniform magnetic field now. Let the field be B bar. I am stressing this again. We are talking only about a uniform magnetic field. Later, we'll solve some questions which will help you understand what happens in a non-uniform field also. Okay. Now this rectangular wire has 4 straight parts. Let's name the corners. On the entire loop ABCDA, the net force is 0. But one of you tell me, how much force acts only on the part AB and in which direction? The length of the rectangle is L. Breadth is B. How much force acts on the side AB?
BIL, sir.
BIL. Okay. The formula is IL cross B because the magnetic field is uniform. For the side AB, the length vector is from here to here and its magnitude is L. Now length vector cross magnetic field. Length vector is in the y direction, magnetic field is in the z direction. So angle between them is 90 degrees. So it will simply become ILB And if you do the cross product, force will be to the left. So the force acting on this side is in this direction. How much it is? I, L, B, where L is the length of that side of the rectangle. Similarly, on CD, if you observe, in CD the current is going down, then the length vector for CD will be this way, downwards. Magnitude is L only, but direction is downwards. And now if you do L cross B, you'll see that the force is to the right, this way. Same ILB will be acting to the right on the part CD. Next, Rishi, tell me how much force and in which direction will it be acting on BC, the side BC? The breadth of this rectangle is B, or take it as B itself, small b. Or just for
IBB.
Okay, yeah, just for convenience, let us call the breadth as X.
IXB on both.
Okay, so you are saying IXB, where B is the magnetic field now, correct?
Yes, sir. Yes.
Okay, and since the current is flowing to the right, magnetic field is inward, the force on that side of the rectangle will be this way, IXB, and force on the lower side of the rectangular loop will be this way, the same IXB. Now the plane, the rectangular loop is in the plane of your screen, and these four forces are also in the plane of your screen. Then
So
this
this is like the tension acting on like the current loop, right? Like DF in the previous question.
yeah, there are DFs acting everywhere. The resultant of those DFs we have considered directly. On every element there will be a force acting. Okay, combining the forces on all elements of each side, this is the net force on each side that we have indicated here. Okay, now you can see that the line of action of these two forces is the same, so their torques will cancel. The line of action of these two forces is same, their torques will also cancel. In this current orientation, in this present orientation, there is no torque also on this loop. Okay, so at the moment the torque acting on this loop is 0. Net force is 0 anyway, as you can see. Whatever force is acting to the left, same force is acting to the right. Whatever force is acting upward, same force is acting downward. Net force is 0. But since their line of actions are same, this line and this line, their torques also cancel. Okay, upward force, downward force, torques cancel. Rightward force, leftward force, their torques cancel. Okay, so in this position, the net torque on this rectangular loop is 0. But let us rotate the loop a little bit. Or, okay, wait, we'll do one comparison with electric dipole. In this case, magnetic field is into the screen. You all are aware of that. B is inwards. In which direction is the magnetic moment of the loop at this moment? I mean, in this position. What is the direction of magnetic moment?
Into the screen.
Into the screen. Okay, so in this position, magnetic moment is also into the screen. Right. Field is into the screen. Magnetic dipole moment is also into the screen. What is the angle between them? 0. They are parallel to each other. Okay, we can compare this to the case of electric dipole placed parallel to an electric field. Okay, suppose there is a minus Q here and a plus Q here. Electric dipole placed parallel to electric field, uniform electric field. We know net force on it is 0. In this particular position, the net torque on it also will be 0. The positive charge will experience force this way. Negative charge will experience force this way. They have the same line of action. Their torques will cancel. Net torque will be 0. Okay. When an electric dipole is parallel to electric field, the net torque on it is 0. And now we see that in this particular example, we have observed that when magnetic dipole is parallel to magnetic field, the torque on magnetic dipole is also 0. Fine. So there is a similarity between electric dipoles in electric fields and magnetic dipoles in magnetic fields. Now let us rotate this dipole by some angle and see what happens. Actually, there's a much easier way to explain this, but I want you to learn both methods. I'll tell you the easier way also later. Now we need to rotate this loop. Just a moment. Magnetic field is still directed inwards into the screen. It's a uniform magnetic field, but the loop has to be rotated this time. So let's say it is rotated by an angle theta, and it now appears like this to us. Just a moment. Okay. So basically when you rotate it, one edge comes closer to us and one edge goes away from us, right? About which axis are we rotating? Let us visualize that first. Going back to the diagram, I am rotating this rectangular loop about this axis. So what I am doing is I am bringing the side AB closer and sending the side CD farther. Okay. So when AB comes closer to you, it will appear bigger, and CD goes away from you, it appears smaller. So that perspective is what I'm trying to show here. So this is the axis about which it was rotated. It's still a rectangular loop, but when we see it like this at an angle, it looks like a trapezium. Okay. And half of the loop is out of your screen and the other half is behind your screen. The half behind your screen, I'm making it dotted. So this is the side AB for us, and that is the side CD. We rotated it. Are you all able to understand what was done? Originally, it was like
Yes, sir.
this. Originally, it was like this. Okay, but now one edge is brought closer to us. The edge AB has been brought closer, and the edge CD has been sent back. Okay, by what angle are we rotating it? Let's say we are rotating it by an angle theta. Okay, on the lower side, I'm showing you the angle theta. Fine. The current is flowing this way. Now, if you observe, see the magnetic field is still the same, right? It is B itself. The current is I. Two sides are still L and L. The other two sides are X and X. Okay, A, B, C, D, their lengths are L and L. AD and BC, their lengths are X and X. Okay, so there'll be a force acting on this wire AB this way. It will be ILB, and there will be a force acting on CD here. That force will be acting like behind the screen. The force is ILB itself, but it is acting. The line along which it is acting is behind the screen now. And what about BC? BC, there will be a force like, okay, there is current in BC. Magnetic field is into the screen. Anyway, the force has to be perpendicular to the wire. No, IL cross B, it has to be perpendicular to the wire. So BC still experiences a force in this direction along this line. AD experiences a force this way. These two forces are still along the same line. So they'll cancel, their torques also will cancel. They won't contribute to torque. But the forces acting on AB and CD, they will contribute to torque. Okay. Let us look at it from above now. Let's say this is the magnetic field. When you look at it from above, the loop looks like a line. Okay. Originally, it was like this. Which side are you seeing from? When you see from above, you will be seeing this side, BC. Okay. So this is B, this is C. And the magnetic moment vector was this way. Original magnetic moment vector was parallel to the magnetic field. Net torque was 0. But now we rotated the loop. Okay, original magnetic moment also I'll indicate in yellow itself. Now we rotated the loop by an angle theta to this orientation. Okay, AB came towards us, CD went away from us. So this is B now, this is C. The magnetic moment is now like this. We rotated the loop by an angle theta, then the magnetic moment will be making an angle theta with the magnetic field, because this is the direction of the field. Are you all able to visualize this? Is it clear? Originally, the loop was in the plane of the screen. Then magnetic moment was perpendicular to the screen, like this. Now, if you rotate the loop by an angle theta, the magnetic moment vector also will rotate by the same angle theta. That is what I'm showing. Earlier, magnetic moment was in the same direction as the field. Now we rotated the loop by theta, so the magnetic moment also rotates by theta. Okay. On AB, there is a force ILB acting. So when you see from above, the force ILB will look like this. And on CD, the same force ILB, which is acting behind the screen, will be like this. They will not be along the same line anymore. Okay. Now BC total length was X. So this part becomes X by 2. Line of action of force is like this. The distance is X by 2. Then this perpendicular distance. Why do we care about the perpendicular distance? Because we are calculating torque. Basic formula for torque is F multiplied with perpendicular distance from the axis to the line of action of the force. The force here is ILB. Perpendicular distance becomes X by 2 cos, okay, not cos, sin theta. That's the torque produced by one force. This other force also produces the same amount of torque in the same sense. Then the net torque on the current loop becomes 2 times of ILB into X by 2 sin theta. 2's cancel. You get I LX B sin theta. Lx is nothing but area of this rectangular loop. So the torque becomes IAB sin theta, which is basically the magnitude of IA cross B. Therefore, you can write torque on a current carrying loop as IA vector cross B vector. A vector is the area vector of the loop. B is the magnetic field in which it is placed. And IA is the magnetic moment. Therefore, torque on a magnetic dipole can be written as M cross B. Magnetic moment cross the uniform magnetic field in which it is placed. Do any of you remember the expression for torque acting on an electric dipole in a uniform electric field? Okay.
Sir,
Huh.
M into B,
What did you say?
MB, sir. MB.
MB అనేవి magnetism లో వస్తాయి. Okay. I'm asking about electric dipole in electric field. Electric dipole will be, I mean, all formulas for electric dipole will be in terms of dipole moment P. And when it is placed in an electric field, the formula will have E as well. So the formula should be in terms of P and E. Okay, anyway.
Sir,
On an
is it P sin theta or something?
it is P cross E actually. Okay, as a vector, it is P cross E. Magnitude is P sin theta. Okay, we had discussed that in electrostatics. So you observe that a magnetic dipole in a uniform magnetic field also has torque given by the same formula. But in place of electric dipole moment, you have to take magnetic moment. And in place of electric field, you take magnetic field. That's all. Okay. See this derivation, if it was difficult for you to follow also, that's fine. Okay, try to do it once on your own, even if you, if you are not able to understand, you can ask me later. But you can directly remember the formula also, it won't harm you. Torque on an electric dipole in a uniform electric field is P cross E. Similarly, torque on a magnetic dipole in a uniform magnetic field is m cross p. Okay, and we know m is NIA. Therefore, in general, torque on a magnetic dipole can be written as NIA cross B. Its magnitude is NIAB sine theta. Where what is theta? Theta is the angle between like if
A
you
and
write
B, sir.
if you write A cross B as AB sine theta, theta is the angle between A vector and B vector. So in this case, it will be angle between the area vector and the magnetic field vector. Okay, that's the torque on a magnetic dipole, or basically a current carrying loop placed in a uniform magnetic field. Now, why did I explain this derivation and all? If you could directly remember the formula, as I said, sometimes, especially in JEE Advanced, okay, they can give you non-uniform magnetic fields and ask you to calculate torque. In that case, you will have to proceed this way. Okay, you will have to find out what is the force acting on each element or each side of the loop. Then based on the rotation, how much is the distance from the line of action of the force to the axis of rotation? Those things you'll have to visualize. Based on that, you will have to derive. Okay. Now, based on this, okay, what is this? When current passes in a loop, a magnetic field can exert a torque on that loop. Okay, can make the loop rotate. And the torque depends on how much current passes through it. Okay. So based on this, they designed the instrument called galvanometer. One of you tell me, what is a galvanometer used for?
For finding out small currents.
To detect small currents. Okay. So basically, it's a device which shows deflection depending on the current passing through it. Okay. Deflection means rotation. Rotation requires torque. Okay. That is why they used this idea to build a galvanometer. Okay. So effectively, what is present inside a galvanometer is a loop having a lot of turns. Okay. So we call it a coil. I should not call it loop with a number of turns. I should say a wire with a number of turns. We call it a coil. Okay. So galvanometer consists a coil, let's say of capital N number of turns or loops. Each turn is called a loop. Okay. Inside a coil which can rotate inside a magnetic field. In fact, this same idea of coil rotating in magnetic field or magnetic field being able to rotate a coil is used in an electric motor also. Okay, you all must have had some experience with motors. Basically, when you pass current, the shaft in the motor rotates. Okay, and then whatever is connected to the shaft also rotates. Fine, that is how electric vehicles work. That is how motors work in general. Cooler motor, fan motor, okay, the water pump motor. Small cars, toy cars, they'll have motors in them. They all work on the same principle. Okay, they have a tightly wound coil inside them, and there are very strong magnets also inside, permanent magnets. So when current passes through that coil, no, that coil is already in the presence of a magnetic field. When current passes through it, the coil experiences torque and starts rotating. Okay, then the shaft attached to the coil also rotates. That will be able to drive the vehicle, drive the fan, whatever it is. Okay. Anyway, you learn about DC motors in engineering in detail. So basically, a galvanometer, as I said, it has a coil of N turns which can rotate inside a magnetic field. Now, what do we want the galvanometer to do? We want the galvanometer needle to deflect, means we want it to rotate proportional to the current that passes inside the coil. If small current passes, we want the rotation to be small. If more current passes, we want the rotation to be more. Okay. Suppose there is a loop. Okay. Consider a loop. Of N turns and area A in a uniform magnetic field B. Okay. If a current I passes through it, then the torque it experiences will be NI AB sine theta. We just derived that, where theta is the angle between A vector, area vector, and magnetic field vector. So definitely the torque depends on the current. It is proportional to the current, which is a good thing. But there is a drawback in this. The torque varies with the angle between the loop and the magnetic field. Now the loop is going to rotate, no? So the area vector won't maintain the same angle with the magnetic field all the time. The magnets inside the galvanometer, they are fixed. So the field cannot be changed. What changes is the orientation of the loop. Okay. When orientation of the loop changes, theta is also a variable. So torque acting on a current carrying coil placed in a uniform magnetic field depends on two variables. Not just the current, it depends on the amount of rotation as well, which is not very helpful for us to build a galvanometer. In a galvanometer, what we want deflection depending on the current. Fine. The angle rotated should depend on the current. And also, this torque will keep on acting on the loop. It will keep making the loop rotate. We don't want that. We want the loop to get balanced somewhere. Okay. Depending on the current flowing through it, it should rotate by a certain angle and stop rotating. So there should be something providing a counter torque. Can one of you tell me how a spring balance works? Basically, what is there in a spring balance? What
So
is
we
there?
have a spring.
There is a spring. There's a spring with a
And
needle attached to it, pointer attached to it. When you connect a block or a mass, the spring stretches, the pointer moves. Based on the stretch, you can tell how much is the weight of the block. So basically, it's like this. We're talking about a spring balance. Spring balance is used to measure the weight of an object. Okay. So inside the spring balance, there is a spring. That's why it's called a spring balance in the first place. And then there's a pan here in which you can put the object whose weight you want to check. And the spring will be connected. The end of the spring will be connected to a needle. The needle points to markings. This is 0 kg, then maybe 1 kg, 2 kg, 3 kg, and so on. Okay, when there's nothing in the pan, the needle should be at 0. When you put something in the pan, obviously the spring stretches because of the weight of the object that you kept in the pan. Let's say there is something placed here whose weight you are trying to measure. Then definitely gravity will pull it down. Maybe it gets pulled down. The gravity will keep acting on it. Under the influence of gravity, the pan keeps going down. What prevents the pan from continuously going down? It's the spring. Okay, so basically what happens? The spring stretches, then the needle goes down, and based on how much the needle goes down, we can estimate the weight of that object. So effectively what happens here is the weight of this object, that is mg, is balanced by spring force, kx. And we write kx is equal to mg. So x becomes mg by k. G is acceleration due to gravity, k is spring constant, which are known to us. From that, and the elongation can be seen, okay, by how much the needle is going down. Then we can estimate the mass of the object. Okay, basically that is how a spring balance works. We have something similar in a galvanometer as well. Now here, in a spring balance, the forces are balanced. Mg, which is the force of weight, is balanced by spring force. In a galvanometer, torques get balanced. First, we make the magnetic field produce a torque on the current carrying loop, which makes the loop rotate in one sense. Then the spring will provide a counter torque to that. And the loop will rotate by a certain extent and settle somewhere. Magnetic torque gets balanced by spring torque. That is what happens in a galvanometer. But first of all, we need torque, which depends only on current, not on the angle rotated. So we cannot use a uniform magnetic field in a galvanometer. That won't work for us, because in a uniform magnetic field, as the loop rotates, the torque changes based on the rotation also, not just based on the current. Okay, we don't want that. We want torque to depend only on current. So to overcome that challenge, what scientists did is they came up with something called a radial magnetic field. Just a moment. Consider something like this. Let's say this is a strong permanent magnet, and assume this is the North Pole. And this is the South Pole. Okay, so there's one magnet to the left whose North Pole is seen here. There's one magnet to the right whose South Pole is seen here. Now there will be a field between them, magnetic field. And because of the curvature, because of the shape, the magnetic field between them will be in the radial direction like this. The field lines will be like this. Out of the North Pole towards the South Pole. Okay. Now you imagine a loop in this, inside this. Just a moment. Let's assume this is the loop of wire having a number of turns. Okay, this is the top view. We are seeing it from above. Okay. So basically when current passes through it, if current passes this way, its magnetic moment, just curl your right hand fingers along the flow of current, the magnetic moment will be like this. Okay. So assume this loop is able to rotate inside this magnetic field. Okay. Now you can see different field lines are at different angles with the loop. But the advantage we have here is, even if this loop rotates by a certain angle, okay, suppose the loop's orientation, like you observe at this instant itself, there is maybe one field line making 30 degrees with it. There may be one making 45 degrees with it. There may be one making 60 degrees with it. Different field lines make different angles with it. Okay, it's a radially directed field. When you rotate this loop, okay, let's consider a separate diagram. The magnetic field stays the same. We are not changing, we are not disturbing the magnets. Okay. Suppose the orientation of the loop changes to maybe somewhat like this. Okay, orientation of the coil, I should say, not loop. Now also you will see that there are some field lines making 30 degrees. There are some making 45 degrees. Okay. Of course, I have not shown all field lines. There will be one making 60 degrees, 30 degrees. So the relative orientation between the coil and the loop stays the same. Okay. Some field lines will still be perpendicular to the coil. Some field lines will be parallel to the coil. Some field lines will be making 30, making 60, and so on. Okay. So if you use a field like this, what happens is the torque acting on the loop, on coil, not loop, torque acting on the coil becomes independent of orientation of the coil. Then the formula will only be NIAB. That dependence on theta, the angle between the area vector and magnetic field, is now gone, because whatever be the orientation of the coil now, there are some field lines at 0 degrees with the coil, there are some field lines at 90 degrees with the coil, and so on. Okay, so this way we can remove the dependence of torque on angle rotated by the loop, and now it depends only on theta. Sorry, only on current I. Okay, so if a current I passes, torque starts acting on it. Now this torque is due to magnetic field, so I'll call it as torque due to magnetic field, NIAB. This rotates the loop. I keep saying loop. This rotates the coil. Okay, coil is a collection of loops. Now, to this coil, assume there is a needle fixed to the axis of this coil. Now, if the coil rotates, the needle rotates along with it. And it can show some reading on the galvanometer. That's the idea. If the coil rotates this way, the needle rotates this way. If the coil rotates the other way, needle will also rotate the other way. Okay. Now the torque exerted by the magnetic field rotates the coil. It keeps on rotating the coil. We want it to stop. So to stop that, what they do is they connect a small spring to this coil. So suppose the coil rotates to the left, the spring gets stretched. It will exert a force this way. It will create a counter torque like this. Okay. Suppose the coil rotates to the right, the spring gets compressed, then the force will be in the other direction. The counter torque also will be in the other direction. Okay. So this torque due to magnetic field will start rotating the coil, and the coil will stop rotating, or the coil will settle at the position where torque due to the magnetic field is balanced by torque produced by the spring. Just like in a spring balance, force of gravity should be balanced by the spring force. Okay. In a galvanometer, torque of magnetic field should be balanced by the spring's torque. Okay. So torque due to magnetic field is NIAB. Torque produced by a spring, we write it as K theta, where K is called torsional constant of the spring. Actually, what happens? No, they don't connect a linear spring like this. They use a spring which can be twisted. Okay, like you just consider a wire. You twist a wire and release it. What happens? It will come back to its original position. Okay, original arrangement. So that twist is called as torsion. Okay, the torque produced when you twist something is called torsion. Okay, so they use a spring like that. Now, as kids, you all must have played with toys which require a key to be twisted. Have you ever
Yes, sir.
played or not? Yeah, it has a coil spring inside it. Basically, when you give the key, when you tighten the key, the spring coil gets tightened. And then as it unwinds, it drives the toy forward. Okay.
So is it also like that pullback cars which we use?
In those pullback cars also that coil spring will be there. Yes. Okay. We call it as a torsional spring. The same thing is used in a galvanometer. Okay. So when the coil of the galvanometer rotates, the torsional spring, it gets tightened. Then it will create a counter torque. Okay. So that's the idea here. Torque due to magnetic field gets balanced by torque due to the spring. Then you can say that theta, the angle rotated by the coil, okay, whatever is the angle rotated by the coil, same will be the angle by which the torsional spring is twisted. Okay, so theta becomes NIAB divided by K, or you can say it is NAB by K multiplied with I. This way, the angle rotated by the coil will be proportional to current in the coil. That is the idea we use in a galvanometer. Okay, so based on its rotation, you can tell how much is the current. Of course, there is a proportionality constant between them. It depends on N. What is N? In all this derivation,
Number
what
of
is N?
turns.
Number of turns in that coil, correct? What is A?
Areas.
Area of each turn of that coil. B is the uniform, not uniform, I should not call it uniform. B is the magnetic field inside the galvanometer. That will be given in the question. Radial magnetic field, we don't have an expression for it. They'll give you that value in the question if they want to ask you. What is K?
Original constant of
Torsional constant of the spring. So the proportionality constant between angle rotated and the current in the coil depends on these factors. Okay. Now, galvanometer is a device used to detect very, very small currents also. So basically what a galvanometer is expected to do is it should show significant deflection even when very small current passes through it. So we want a galvanometer to be a very sensitive device. Okay, even for small currents, it should show significant deflection or rotation. So we define something called current sensitivity of a galvanometer. And how is current sensitivity defined? Angle rotated per unit current. Okay, angle rotated delta theta per unit change in current delta I, or you can write d theta by di. This quantity is what we call current sensitivity of a galvanometer. Okay, it makes sense, no? More angle rotated for small current, sensitivity will be high. Okay, like if angle rotated is more for small currents, the whole sensitivity value will be a large value. That way it makes sense. So remember, d theta by di is what we call current sensitivity. And how do you get that? We know theta is equal to, like we just derived, theta is NAB by K into I. Okay, this whole thing is a constant. So from this you can say d theta by di is simply NAB by K. So this is what is current sensitivity of the galvanometer. They may ask ratio based questions depending on this. They can give you two galvanometers, tell you what is the ratio of the number of turns, ratio of areas, ratio of torsional constants, and ask you what is the ratio of their current sensitivity. Or they may ask you how to increase current sensitivity, decrease current sensitivity, how to double it, triple it. Such questions can be asked. Okay, not a big deal, easy to solve. Then there is something called figure of merit of a galvanometer. It is just the inverse of current sensitivity, di by d theta, which becomes K divided by NAB. Okay, current per unit deflection, that is what we call as figure of merit. So remember, they are reciprocals of each other. Okay. Fine. So let's quickly go through what all we discussed today. Conversion of galvanometer to ammeter, questions based on galvanometer, those things we'll discuss in next class. So yeah, first we discussed this tension based problems. Then we moved on to torque experienced by a current carrying loop in a uniform magnetic field. Okay. We did that elaborate derivation where we imagined we considered a rectangular loop. We found forces acting on each side of the rectangle. Based on that, we wrote an expression for net torque. Okay. You don't have to do all that. If it's a uniform magnetic field, you know a current loop behaves as a magnetic dipole. So based on the formula for torque experienced by electric dipole in uniform electric field, you can directly write torque experienced by magnetic dipole in uniform magnetic field. So for a current carrying loop, M cross B changes to Ni A cross B. That's all. We proved that in case of that rectangular coil also. But in case the field is non-uniform, you will have to calculate torque this way. Okay, you'll have to imagine forces acting on each element. Okay, calculate torque produced by each element and integrate that to get the net torque. Next, we saw how that concept is used in a galvanometer. In galvanometer, the field that we generate, the magnetic field we generate, is not a uniform magnetic field. It is a radial magnetic field. Why are we using a radial magnetic field? Because we want the torque acting on the coil to be independent of angle rotated by the coil. So if you have field lines in all directions, whatever is the orientation of the coil, you will still have field lines in all directions. Okay, that way the torque will become independent of angle rotated theta. It will depend only on the current I. Whose torque? Magnetic field's torque. Depends only on current. That is balanced by the torque produced by the torsional spring. So NIAB is equal to K theta. Based on that, you will get. Okay. Fine. Tomorrow I'll be sending you a worksheet. Next class you will have on Tuesday itself.